Hello everyone, welcome back. This is Dr. Blinch from 2024, and now we're going to talk about memory. We have two modules on memory, and in the first module we're going to talk about sensory memory and working memory. So there are three memory systems. Again, the first two we'll talk about today, and long-term memory will be our next module. So there are trade-offs between these systems. So sensory memory, for example, has an infinite capacity, so it's a literal copy of what we say see or hear, but the expense of being that detailed is that it decays very rapidly, and we'll see how rapidly soon, but it can be a matter of seconds. So working memory, the longevity is a medium duration, so longer than sensory memory, but the trade-off there is that the capacity is decreased. So it's no longer a literal copy of the environment. Now long-term memory, it's potentially everlasting, so you do have some memories that last forever, and thankfully it is potentially unlimited in storage. And I like to remind myself that when I'm studying content, especially for say final exams, and I'm thinking, can my brain hold more information? Yes, it is potentially unlimited. Here's a very basic schematic of our memory systems, and as we go through, this will become more detailed. So we have our sensory input, so think of all of our sensory information coming in, and that goes immediately to our sensory memory. And this is a memory system you may not have heard about before. So from sensory memory, this is like a literal copy of our sensory information. It, through attention, will go into our working memory. Then from working memory, if our brain decides that, yes, this is information, I should remember it, then it gets consolidated into long-term memory. Now things that are in long-term memory, so if I ask you, what did you do on your last birthday? We extract that information from long-term memory and it comes back into working memory so we can think about it and process it. So working memory is this very important middle system that interfaces with sensory memory and long-term memory. Now after these two modules, we're going to have a much more detailed concept of these three memory systems, and it will eventually look like this. But we'll take this one step at a time. So this is our starting spot. So let's talk about sensory memory. It's the most recent discovered memory system, and there's kind of the least amount of studies on it. So sensory memory was discovered by George Sperling, and kind of a fun story here. Let me refer to my notes so I get the details correct. So George Sperling, he started his PhD at Harvard in the late 1950s. He was in the Department of Social Relations, and he was very excited for the first summer because that's when they got to run their first experiments. But unfortunately, he had failed some of his classes in that, the fall and spring semesters. So the Department of Social Relations said, okay, well, if you failed your classes, you're probably not ready for research. So come back next year, redo those classes, and then next summer you can do research. And that didn't sound good to George because he was very excited for experiments. So he came up with a creative solution. He realized he could transfer departments. He actually transferred into the Department of Psychology, and they kind of treated him like a new student. They said, okay, well, welcome, George. This is your first summer, and this is when people start running experiments. We don't really care about those courses in social relations. They're not applicable to psychology. So go ahead and run a psychology-based experiment. And that experiment ended up, evolving into his dissertation, and it was the discovery of sensory memory. So a great, transition from failure to success. Something I like to think about, sometimes when I fail at things that, well, maybe this will lead to an important success. All right, so what was Sperling trying to do? He actually had a fairly straightforward experiment, kind of practical. He wanted to know how much information can the visual system take in during a single fixation. So the eyes mostly do two things. They fixate, so they're still, they look in one place, and then when you want to look somewhere else, they jump, and we call that a saccade. So they jump to look at something else, and then you jump and fixate, jump and fixate. So the saccades are very important because that allows us to look at different places. However, the fixations are maybe the more vital part because it's only when our eyes are fixated that we pull in conscious visual information. There's some neat studies that show when we saccade, we're actually not conscious of information during that time. So Sperling was looking at these fixations, and he knew that fixations typically last between 50 to 200 milliseconds. And he wanted to know in a single fixation how much information got into your visual system. So let's look at the experiment he designed to test this. So he had a display, and we'll look at how this was done. And in that display, 12 random letters would come up, and they would flash on and off within 50 milliseconds, so the duration of a short fixation. In this first condition, he asked participants to recall as many letters as possible immediately after they disappeared. And he called this full report because you're trying to report all the letters. So perfect performance, you would report 12 out of 12 letters correctly. Now, to see these 12 letters, he had to use a special visual display called a tachistoscope. And we can't really emulate this in PowerPoint, and we'll talk about why. But within this tachistoscope, and this is maybe a little bit like if you've ever been to the DMV and looked in those devices where they test your vision, it's kind of like that. And the key here is that it's displaying those 12 letters to your central vision, where they should all be visible. They should all be clear and within your focus. So we can't really do that in PowerPoint, but I'll show you here what it kind of looked like, although remember we're not using a tachistoscope. So the 12 letters would appear and disappear, and you'd be asked to report as many as possible. Now when we do that here in PowerPoint, you're probably saying, well, I didn't see all the 12 letters. And again, that's because we don't have a tachistoscope, and let me explain. So if you think about your visual field, so we can see about 100 degrees off center in both directions, but it's really only the central vision where we see clearly. So if we look at this music example, so if you're looking at a sheet of music, and if you're fixating right in the middle, well, the only parts you can see clearly are kind of plus or minus 5 degrees within central vision. Further away from that, you're not blind, but you just can't, read text or read letters within, your peripheral field of view. Your peripheral field of view is really great at, say, detecting motion, maybe even better than your central visual field. So it has its uses as well. But if we want to see something clearly, like if we want to read letters, then we need to fixate on those letters so that they're within central vision. So the tachistoscope, what it does is it made sure that those 12 letters were all within central vision. So think of this as that plus or minus 5 degree radius where you can see information clearly. Now in contrast, when we do this on PowerPoint, and it would depend on the size of your screen and how far you are from it, but probably to read each letter you'd have to fixate one at a time. So if you want to read the O clearly, you'd fixate here, you could see the O. The next letter, you could see that there's something there, but you wouldn't be able to read it until you saccade and then fixate on that. So the reason this doesn't work on this screen is because you'd really need to do 12 saccades and 12 fixations to see all 12 letters. And there's not enough time for that in 50 milliseconds. So the tachistoscope was vital so that all 12 letters could be clearly, visibly seen within 50 milliseconds. All right, let's go forward. So what happened? Remember, you're trying to report 12 letters. And what he found was, on average, participants could report 4.5 letters. That doesn't mean anyone was reporting half a letter. It could be that half the participants could report 4, half the participants could report 5, so on average it's 4.5. He converted this to a percentage, so 4.5 out of 12, so think of it like your score on the test. So participants were reporting 37.5% of the letters. And Sperling called this the immediate memory span. Okay, so it seems pretty straightforward. And the interesting part here comes from what participants told him. They said, well, I could see all the letters, and that makes sense because they're all within the central vision. But they said, I just couldn't report them all. And that seemed like a weird contradiction. How can you see them all and not report them all? And Sperling came up with two hypotheses. We'll look at those, and then we'll look at the experiment he used to test them. Okay, sorry. Here is the experiment that he used, and we'll talk about the hypothesis next. So here, what he did is, again, there were 12 letters that flashed up for 50 milliseconds with the tachistoscope. But here, he called this condition partial report. So a cue was given after the letters disappeared, indicating which row of letters to recall. So think 12 letters come up, they disappear, and then he might say top, and he wants you to report the 4 letters in the top. Or he might randomly say bottom, and then you need to report the 4 letters on the bottom. So you don't know which row he's going to say in advance. So you're still trying to remember all 12. You then only have to report the top 4, the middle 4, or the bottom 4. So as an example, and again, we don't have a tachistoscope, so the letters appear and disappear, and then randomly on this trial, he said to report top. So perfect performance, if we go back, it would be if you could report S, J, T, and P. Okay, here are his hypotheses. So Sperling thought, well, maybe what happens is when we look at the real world, there 12 letters appear, but maybe only a subset of the real world makes it into memory. And maybe that happens to be 4.5 letters. So if participants, if that's the case, in this condition, participants on average in partial report should only be able to report 1.5 letters. So let's say these 4.5 letters made it into memory. If you were asked to report top, you would know 2 of them. Middle, you would know 1, and bottom, 1.5. So if we average this, 2 plus 1 plus 1.5 divided by 3 is 1.5 letters. So if memory, and we'll see, eventually we'll call this sensory memory, is a subset of the real world, then in partial report, he's predicting that you'll be able to report 1.5 letters. Alternatively, his second hypothesis was, well, maybe all 12 letters do all make it into memory. Now, the reason you can't report all 12 is maybe that information decays rapidly. So it all comes into memory, you see it for a moment, but it begins to decay. So the participant is trying to report these letters before they decay. Let's bring that back for a second. Okay, so imagine this is in my memory, it starts to decay, and I report X, H, E, G, and half of F on average, but then the information is gone. That could explain why the participants saw all 12 letters but couldn't report all 12 letters. Now, if there was enough time to report 4.5 letters in full report, in partial report, there should be an ample time to report 4 letters. So imagine, the letters appear, I'm given the cue to report middle, okay, F, G, H, E. I should have time to report all 4 letters. So if memory, sensory memory as we'll see in a moment, is a literal copy of the real world that decays rapidly, in the partial report condition, Sperling predicts that participants should report 4 out of 4 letters. Okay, so what happened? Well, he found that participants could report almost every letter in the cue row. So on average, scores were 4 out of 4. This supports hypothesis 2, that memory is a literal copy of the real world, but then it decays very rapidly. Now he called this a partial report superiority because partial report had better performance than full report. Now it's not the number of letters that made it superior, because remember, full report you remembered 4.5, partial report you remembered 4. So 4 doesn't sound as good as 4.5, but remember it's 4 out of 4, which is 100%, and that's better than 4.5 out of 12. So because you could remember every letter that you're supposed to in partial report, we call this a partial report superiority. Now the conclusion here, following hypothesis 2, is that sensory memory for vision, for example, is basically a snapshot of our last fixation. So when we look somewhere, all of that visual information makes it into sensory memory, but then it decays very rapidly. For vision, you can kind of think of it like a reverse Polaroid. So you know a Polaroid picture, you take a picture and then it fades in? Well, it's doing the opposite here. So imagine you fixate, it's like a Polaroid appears in your brain with all that visual information, but then it rapidly decays. So if we go back to our two hypotheses, the results here supported hypothesis 2. Sensory memory is a literal copy of the world that then fades very rapidly. Sperling did a follow-up experiment, as all good scientists do, and he wanted to know, well, how long does that snapshot last? And we know it lasts for 4.5 letters, but that's not the best metric to measure duration. He wanted to know how long in milliseconds. So what he did here is he added a delay between the disappearance of the letters and then when he when he told you which row to report. So it was partial report, but there could be a gap between the letters disappearing and him telling you which row to report. So previously we saw that as soon as they disappeared, you were told which row to report. So imagine here you're told to report the middle row. And kind of an easy manipulation, but what you can do is you can add in time here. So you can have the letters disappear, and then a few seconds could go by before you're told which row to report. And here the idea is you're told to report the bottom row. Now he used some fancy math here to support his findings, which we won't worry about. But basically what he found is that he looked at how long a delay can you add until the partial report superiority disappears. So he's going to keep adding more and more of a delay until partial report and full report have the same performance. And what he found is that that delay could be up to 500 milliseconds. And he concluded, with some fancy math, that the snapshot, the visual snapshot, lasts about 500 milliseconds. So imagine every time I fixate, that information, everything gets into my brain, my sensory memory, and it lasts for about 500 milliseconds, half a second. Now sensory memory, Sperling famously studied visual sensory memory, and that memory system is also called iconic memory. And we know, still today with even more research, that yes, it does last about half a second. The auditory system has its own sensory memory. It's also called echoic memory. And one neat thing about it is different than the visual system is it lasts about 10 seconds. And you've probably all used your sensory memory before. And auditory sensory memory, maybe this example will ring a bell with you. So have you ever been in a class, for example, and maybe your attention is drifting away, but then the instructor says, and that will be on the test? And immediately you kind of go, oh, now I'm paying attention, and oh, what did they say? And somehow in your mind you can hear the last few seconds of what they said, even though you weren't paying attention in that moment. That, for example, could be your echoic memory, your auditory sensory memory. Another one that I come across is sometimes when I'm talking to my wife and she's distracted, maybe trying to help the kids or do 3 things at once as she's always doing, and I tell her something and she looks at me and says, oh, I'm sorry, I didn't hear you, and then I'll just look at her and wait for that sensory memory to kick in. It's almost like a 10-second recording that we all have in case you missed that information the first time. Now the hypothesis is that we have sensory memory for each of our sensory systems. There's been a little bit of research on the tactile system, not very much, so it hasn't been named yet, and perhaps that's something that you could name in your PhD dissertation. Now why do we have sensory memory? Is it really needed at all? Well, the idea is that it gives us a second chance at processing information. So in the auditory examples, Your ears are pulling in information even though your attention might be somewhere else. And if suddenly you realize you need to attend to that sensory auditory information, you can go back and hear the last 10 seconds. For visual information, there's actually many times every day, countless times, where we need that backup. An example of that is when we blink. So we blink a lot, and when we blink, we don't have this conscious experience that the world goes dark unless we close our eyes for longer than a normal blink, and it's our brain kind of fooling us. So when I blink, and my brain says, "Oh, what's happening in the world?" It says, "Okay, well, there's no vision now. Hey, but I have this snapshot that lasts 500 milliseconds, so I can use that when I don't have real-time visual information." Now, remember how I said when we saccade that we don't have conscious visual information? So when we saccade, and we do this countless times in a day, we don't suddenly think that the world has disappeared, and it's again likely because we can use our visual sensory memory to fill in the gaps during those short periods of time. And because blinking and saccades are short, that is likely why the visual system sensory memory is only 500 milliseconds. You might think, well, wouldn't it be helpful if we had 10 seconds of past visual information? And the problem there is visual information is highly dynamic in real time. Think about an athlete. If they blink, yes, it's good to be able to refer to what they saw 500 milliseconds ago, but they wouldn't probably find it very useful to also be able to go back to 10 seconds ago. Because what you see 10 seconds ago, say on the basketball court, is probably not relevant to the decision you need to make now. Now, auditory information can also be very dynamic, say for a musician, but in most cases outside of that, it seems to be helpful to have a longer duration auditory sensory memory. So it seems they've evolved to have these different durations. All right, so we've covered sensory memory, and all we're actually really going to add at this point, so it's going to stay as kind of one component, sensory memory. We do know that every modality would have its own sensory memory, and we can think of it as a snapshot, and that description is really best for visual sensory memory. For auditory sensory memory, that would be more like an audio recording. So next, let's look at working memory, and here I'm just trying to show that some people refer to this middle memory system as working memory, others refer to it as short-term memory. And those are largely interchangeable. The working memory research we're going to focus on, done by Baddeley. He was the one who kind of really introduced and popularized the terminology of working memory, so we'll stick with this. But if in other classes or out in the world, if someone says working memory, short-term memory, mostly mean the same thing. Researchers, of course, argue about this. And here are different possibilities for the relationship between working memory and short-term memory. So B here, it says, they're exactly the same thing, they just have different names, right? Two names that mean the same thing. Or they could be completely different. So A says, yes, short-term memory is one thing, working memory is another. C and D show overlap. So maybe working memory is everything in our middle memory system and short-term memory is a part of that. Or vice versa. And there are other models to what the relationship is between short-term memory and working memory. We're not going to worry about that. We'll just kind of stick with working memory for now. So what is working memory? Well, a few examples here. So it has kind of a medium duration. So it lasts longer than sensory memory, but definitely not this kind of like everlasting resource that is long-term memory. We're usually talking about durations of seconds to minutes kind of range. It's temporary storage. So if someone, say, tells you a phone number and you need to remember it for a moment until you can put it into your phone, you're holding that information in your working memory. Now, it's also where we process information. And we'll see examples of this. But if you're thinking about something and you're processing it, if you're manipulating that information, we're doing all of that in working memory. You can also think of it as your attentional focus. So if your eyes are open, all that visual information comes in. We then decide what do we want to focus on. And that information is taken from sensory memory and brought into working memory. We'll look at this with examples. Working memory has multiple components, and we'll see this as well with long-term memory. The components within working memory, we have a central executive, and then below it we have two subsidiary storage systems. One is called the phonological loop, and one is the visual spatial sketchpad. And we'll talk about these in turn with examples. All right, so the central executive, it's in charge, as you can kind of tell from the name. It's our attentional control system. So it focuses attention. So think of all that visual information coming into sensory memory. The central executive then can decide, ooh, this is important, let's bring that into working memory. It can switch between tasks and divide your attention. It will decide, okay, this visual information, let's bring it in. Where do we put it? Does it go into the phonological loop, into the visual spatial sketchpad? It's in charge of that. It also connects with long-term memory. So, someone asked me, what I did yesterday. Okay, go to my long-term memory, pull that out, put it in the right subsidiary storage system. And this part is, so important that some think it's actually like a fourth component of working memory. That hasn't quite been, well, there's some debate still on that. So here I've just included it as part of the central executive. But there are some researchers who refer to the link between working memory and long-term memory as the episodic buffer. Okay, so we've got our central executive, but we'll focus more on the two subsidiary storage systems. The first is the phonological loop. Now it stores verbal information. So if someone tells you their phone number and you're verbalizing those digits, 806, so on, that's verbal information, and that would be stored in your phonological loop. There's two parts to your phonological loop. There's the phonological store. Think of that as like the memory where the verbalizable information goes. And then there's also this, what's called an articulatory rehearsal mechanism. Yes, I know they have very fancy names for all these components. So if you put information in your phonological loop, say a phone number, it will last for about 30 seconds without any sort of rehearsal. But if you are, say, 5 minutes from your phone, what you'll do is you'll say that information over and over to yourself, and that is what we call your articulatory rehearsal mechanism. And every time you re-say that phone number, it refreshes it so that it will last for another 30 seconds. So that's helpful so that you don't have to say the number over and over as fast as possible. As long as you say it, say every 10 seconds or 20 seconds, it should stick around within your phonological loop. All right, lastly, your phonological loop can hold 7 plus or minus 2 chunks of information. Now, 7 is the average, plus or minus 2 is the range. And what that means is within the population, just like some people are of average height, and there's people who are taller, people who are shorter, we see the same thing with the capacity of your phonological loop. Most of us can hold 7 chunks of information, but some people, their phonological loop is smaller, can only hold 5 chunks. Others have a larger phonological loop, and maybe they can hold 9 chunks of information. And that 7 plus or minus 2 comes from this very famous paper by George Miller. And this was actually, before the concept of working memory. This was in terms of sensory memory, but there's a lot of shared components between these two, this terminology that we'll consider synonymous. All right, let's try using our phonological loop. So here we have 8 digits, yep. And what I'm going to ask you to do is try to remember those 8 digits. They're going to clear off the screen in a moment. So, verbalize that information, put it in your phonological loop, and then say it over and over to yourself so that it will last for 30 seconds. Okay, are we ready? Here we go. Okay, I think that was about 30 seconds. I don't have a clock. I was just counting in my head. So did everyone remember the 8 numbers? And that could be slightly larger than the capacity of some individuals' working memory. So it's 8 digits, it's just a little longer than 7. The other thing this example shows is I'm guessing at least a few of you thought about this number as a date. So you might have thought, oh, sorry, I forgot to change this to a 1. So you might have thought 9/12/2001 or September 12th, 2001. And I tried to do this to 2001 so that it might line up with birthdays in this class. Now, if you thought about it that way, what you did is you actually chunked the information. So this can be a bit hard to remember because it's 8 chunks. 8 individual pieces of information. But if you put them together like this, well, this is actually now only 3 chunks, which would be much easier to remember. And you could potentially remember, 16 numbers this way if you made them into 2 dates, which would be, 6 chunks. So that's an explanation of what chunks are. And we'll see a little more of this later. We're going to look at memory athletes that have learned to chunk as much information as possible so that they can remember more. Now, their capacity is still 7 plus or minus 2, but the idea is that with training, it's not too hard to think of, okay, well, these 2 numbers become 1 chunk, but can you make 10 numbers 1 chunk? Can you make 100 numbers 1 chunk? That might be difficult. But with practice, you can actually do this. We'll come back to that in a moment. All right, what is the Visual Spatial Sketchpad? So it stores both spatial information and visual information. And there was a debate for a while, is there a visual sketchpad and a spatial sketchpad? And it seems like no, there's one sketchpad, a visual spatial sketchpad that holds both types of information. So any sort of spatial information that requires imagery is stored within your Visual Spatial Sketchpad. So if you imagine, say, thinking about, in your mind's eye, your room and the path to the kitchen. So you think about going out your door, which way do you turn, how do you get there? You're doing that with your Visual Spatial Sketchpad. Just like the phonological loop, there are 2 parts to the Visual Spatial Sketchpad. There's the memory, that's called the visual cache, and then what we saw before, the reticulatory rehearsal mechanism. Here, that's called the inner scribe. So imagine, you're trying to remember, say, a shape, and then as you see that shape over and over, imagine you've got an inner scribe that's redrawing that shape to keep it within memory. Another different thing about the Visual Spatial Sketchpad is it, on average, holds 6 plus or minus 2 chunks of information. So this is our first kind of source of evidence that the phonological loop and the Visual Spatial Sketchpad are indeed different, is because they have different capacities. Phonological loop was 7 plus or minus 2. The Visual Spatial Sketchpad is 6 plus or minus 1. Here's a very famous task, an experimental task that you would use your Visual Spatial Sketchpad for. This is the mental rotation task or mental rotation test. And the way it works is you're given a target shape and you're asked, okay, is 1, when rotated, the same as A, B, or C? And this is really hard. And there's a big difference between individuals on this task. Some people find it easy, most people find it challenging, and some people find it very difficult. So here, I think 1 and A are the same. I wish I had my notes. And then 2, oh, I do have my notes. 2, I cheated here, I saw my notes. 2 is the same as B. This is actually an easier version of the real test. In the real test, there's a target shape and there's 4 alternatives, and 2 of them will match. And you only get a point if you can figure out the correct 2. The other thing that makes it harder is there are 12 of these problems, and you're only given 3 minutes, which is basically not enough time. So it's very stressful. You're trying to do this as quickly as possible, even though it's very hard. Now, if you've ever heard before that males are better at spatial abilities than females, that's an overgeneralization. Really, we should say that males, on average, are better than females at mental rotation. And that famous finding comes from this task and other similar tasks. So I've done some research with this task, the more difficult version. And in our results, we found that females, on average, took 21 seconds to solve each problem. And males, were better. They only took 18 seconds. Now, these are the averages. It's not that every male was faster than every female, but the averages were different. So there were some females that were faster than some males. And again, a good analogy here is the height of males and females. So on average, males are taller than females. But it's not every male that's taller than every female, right? There's a lot of overlap. And there are females that are taller than some males. Same thing here. So yes, there's a sex difference, but it's not an astronomical difference. Now, we developed actually a different version of the mental rotation task that was more fun and that we could adapt to test children as well as older adults. And this is the brick building task. So we give you, a very simple Lego model. It's not the kind of set you would, buy, but a very simple model. And then we have some pieces out here, and you need to find the pieces that make that model and assemble it. Now, this task requires lots of skills. So there's visual search, there's the dexterity component. You got to, pick up the pieces, put them together. But part of what this task requires is mental rotation. You need to see, for example, where that, pink piece is, and how it fits with the pieces around it. We can make this task easy so that we have two-dimensional or kind of flat models, ones that with a single view you really can tell how it's put together. And then we use those same pieces, but we have a more complex kind of 3D model, where to build this you're going to have to pick up the model and rotate it to really understand how all those pieces go together. Now, we replicated the sex difference found with mental rotation. Here, on average, females built the models in 74 seconds and males built those in 60 seconds. One confound here is, okay, well, do the sexes have equivalent experience with Lego as children? And that's very hard to say. I think Lego is more and more a gender-neutral toy, but it's possible that male children might have more experience with Lego than female children, on average. So that's a difficult confound to pull out of this task. Now, as we're talking about these examples from some of my research, another thing that we've looked at is jigsaw puzzle solving. And again, like the Lego, lots of things involved: visual search, the actual dexterity of picking up pieces, memory of what you've seen and where you've seen things, but also mental rotation. The fascinating thing about this puzzle task is that we found that females are better than males. So there's a sex difference favoring females. Again, it's not that every female was better than every male, but on average, females had better performance. So when we gave participants these puzzles, and we had a range of puzzles from fairly simple to very complex, This did have, tiny differences in the colors, so it's not as difficult as it might look on screen. So females could solve the puzzles in 235 seconds on average. Males were worse. They took longer, 278. And we're trying to see here, okay, well, males have an advantage for mental rotation, which is one thing you need for puzzles. So what is it that females are better at, which is, not mental rotation, that gives them an advantage here? And that's something we're chasing down. Okay, a lot of digressions there into some of my research. But let's come back to something I alluded to earlier, the World Memory Championships. And these individuals, they're trying to remember a ton of information very quickly. So they're not using their long-term memory. If you ask them the next day, hey, what do you remember? It's probably mostly gone. So what they're really doing is temporarily storing information in working memory. Let's take a look at this example of an individual showing the card exam, the card test, where you're given a shuffled deck of cards, and as quickly as possible you're trying to remember those 52 cards. So check out that YouTube link, watch this video, and then come back here. So here are some of the events in the memory championships. So you're given this book of pictures of people and their names, and these would be made up. They wouldn't be famous people, so very hard to remember. And you're given 15 minutes to memorize 135 faces and names. And the record here by Nelson Dellis, I think this is Nelson Dellis here, is 235 points. So I think a perfect score would be 270. So he has remembered almost every single name and face. Speed cards, the one we saw in the video, memorize 52 cards as quickly as possible. The world record by Alex Mullen is 18.7 seconds. I think that's really impossible because I picked up a deck of cards and tried to just see every one in 20 seconds, and for me it was impossible. You'd have to practice just getting good at flipping the cards, and then you'd also have to get good at memorizing that information. Speed numbers, so shown here, you're given 500 digits, a lot of information, and you have 5 minutes to memorize those. So a perfect score would be 500, and the world record is 483. And this one is very hard. One, there's a lot of information, as there are on the other tasks, but numbers, it's very hard to remember this unimaginable stream of digits. And that's why in the video we saw the technique where you turn, a boring card into something more memorable. Like he said, one of the cards was Kate from Lost. And then the other thing too, to chunk that, is you might put two cards together. So if there's Kate from Lost, and then the next card, say he thinks of it as a blender, well, he might think, okay, Kate from Lost is using a blender. And that is chunking those two things together and making them more memorable. And you can make it more extreme, like it could be Kate from Lost, grinding her hand in a blender, because that's a more evocative image, and you're more likely to remember that. So digits are very challenging, but participants will have some sort of scheme where they turn sets of digits into a visual image. And I remember reading about one athlete who was a track runner at some point in his life. So when he saw digits, he would think of track times. So he might say, 5:28. Well, maybe that's 5:28. Maybe that's a time to run a mile. I'm not sure. But he would chunk them in that way. And that for him was more memorable. All right. So how do we know that the phonological loop and the visual spatial sketchpad are in fact separate storage systems? Because it might just sound like, well, yes, verbal information, visual, spatial, but how do we know the brain actually treats those differently? And evidence from that comes from this huge area of dual task studies. And there are many of these. Oops. So the basic logic to all these experiments is that if you do two things at once, so say we have a task that requires the phonological loop, maybe you're remembering a phone number, and you have a task that uses a visual spatial sketchpad, maybe you're building a Lego set, then there should be no interference between those. You could do either one of these on their own as well as you can do them together because they're using different resources within working memory. Now, there will be interference if you try to do two things at once with the same working memory resource, and they're so difficult that they exceed your capacity. So let's say you're trying to build a Lego puzzle and you're trying to do those mental rotation problems. Well, that's going to overload your visual spatial sketchpad, and you're going to get worse at those tasks, or at least one of them. An analogy here, a more physical analogy, is let's say you're trying to wield a sword. Well, you should be good at that. And if you want to wield a battle axe in your other hand, we'll say that this person's practiced and coordinated. They can do that. So they're using different resources, their left hand and their right hand. But if we say, okay, now you need to wield both weapons in the same hand, that's going to overwhelm the capacity of their hand, and their performance, their dueling abilities with those swords, will decrease. There'll be interference. So Alan Baddeley did a lot of these dual task experiments, and he was really the one who came up with working memory and this idea of these resources. How he came up with this study is there was one time he was driving and he was listening to a football game. I don't know if it was Texas Tech, but we'll assume it was. And what he realized is that both of these resources required the visual spatial sketchpad. So he's listening to the football game, and from the announcer's description, he's imagining where the players are and how they're moving. So that's, visual spatial information. Now, driving is also a visual spatial task. So you need to, focus on where you are, where the lines are, and, stay within them. It's part of the task of driving. And what he found is if he focused on the football game, if he was really trying to think about where the players were, he would start to swerve in and out of the lanes driving, which of course is not safe. And instead, if he focused on driving, which is important, he then couldn't follow the football game very well. And he said, okay, well maybe these are both competing for my same, working memory resource. And it's a great hypothesis, but of course, you need to run an experiment. You need to test naive participants, because Alan Baddeley is obviously very biased from thinking about working memory probably for a good portion of his life. So there's many experiments by Baddeley, but we're going to look at one by Beach just because I quite like the tasks that he used. So there were three tasks. There was the visual spatial matrix task, and these are all nicely named because this will require your visual spatial sketchpad. Okay, great. Makes sense. What did it look like? Okay, so what would happen is there was a 4x4 grid on screen, where I just monitor in front of the participant, and in one of those locations was a star, and that was the starting location. You would then hear an audio recording that would kind of tell you a path to take through this matrix. So here's an example. So this wouldn't be on the screen, you would hear this. So let's say in the starting square, that's where the star is, put a 1. So in your head, you would have to, with your visual spatial sketchpad, imagine a 1 here. In the next square to the right, put a 2. So now you're going to have to imagine, I'm pointing, a 2 in this square. In the next square up, put a 3. Okay, there's a 3 here. In the next square to the right, put a 4. Hopefully I'm doing this properly. In the next square down, put a 5. In the next square down, put a 6. In the next square to the left, put a 7. And the next square down, put an 8. So you're trying to remember this path through this 4x4 matrix. And as soon as that last sentence was played, you would be given a 4x4 grid, and you're told to write down those numbers 1 to 8. So hopefully, if you got it right, you would write this down on your grid. So you're remembering these numbers, but the important thing is kind of the spatial path of these numbers. So for that, you're going to use your visual spatial sketchpad. All right, should we try one here now that we know how it works? Okay, so it's the same starting square, but it would be random on different trials. Let me get the right one here. Okay, so try to imagine where these are going. In the starting square, put a 1. In the next square down, put a 2. In the next square to the left, put a 3. In the next square down, put a 4. In the next square to the right, put a 5. In the next square to the right, put a 6. In the next square up, put a 7. In the next square to the right, put an 8. Okay, so now try to write that down. Let's see. You ready? So did we get it? Hopefully you could. Hopefully you understood the task. Participants would be given some practice because the first few times you're not going to be as good just because it's new. All right, so the visual spatial matrix task requires the visual spatial sketchpad. Now the next task was the verbal matrix task, and it requires the phonological loop because it's verbal information. So what he did here is he tried to come up with something that has similar structure to the previous task, but it wasn't going to involve a spatial path. It just requires remembering a series of words. So what this looked like is it would start just like before. In the starting square, put a 1. Although there was no grid, there was no star, so you actually don't have to remember anything for this sentence. The next sentence would have the same structure we saw before. In the next square to the quick, put a 2. And the quick is the important part here. So you need to remember that the first word to remember is quick. In the next square to the good, put a 3. So this first part is really just the same structure over and over. It's going to go, 1 and on, and you're just trying to remember these words in the correct order. In the next square to the quick, put a 4. In the next square to the bad, put a 5. In the next square to the bad, put a 6. What they found in pilot testing was that this task was harder than the visual spatial matrix task. So the visual spatial matrix task went from 1 to 8. The verbal matrix task, because it was harder, only went 1 to 6. And there is some logic to this as well. So the visual spatial task, which had up, down, left, and right, here those words were changed from up, down, left, or right to quick, slow, good, and bad, to try to kind of balance the structure to both. All right, shall we try this one? So after these were read out, you would be then given a piece of paper, and you would write down those 5 words. All right, let's try this. Make sure I have a new one here. Okay, just don't want to do the same one twice in a row. In the starting square, put a 1. In the next square to the bad, put a 2. In the next square to the quick, put a 3. In the next square to the bad, put a 4. In the next square to the quick, put a 5. In the next square to the quick, put a 6. And you'd have to remember those, and then you'd be given the paper. So you can't just write them in as they're read out, which of course would be very easy. All right. Oops. Oh, where are the answers to that? Okay. So there are the answers. Hopefully you got that one right. Again, participants would get a little bit of practice so they'd warm up to these tasks. Okay. Third task, last task here, was a spatial tapping task. Now this requires the visual spatial sketchpad because you're trying to move your finger in a spatial pattern. And I made up a version of this task with Lego blocks. They use just wood blocks, but it would look something like this. And what you're told to do is you start and you tap this first block here, and then you'd work your way over to the right, and then do the next row, next row, next row. So you'd tap across these blocks, and then when you got to the end, you would then kind of reverse and tap back. So you'd start in the last one, and now you'd tap to the left, finish this row, go up to the next row, and so on and so forth. And if you made it back to the start, and the other task, the visual spatial matrix or the verbal matrix was still going, you would just keep tapping this pattern. Okay. So those are the 3 tasks, and there were 4 conditions. So there were single tasks, so just do the visual spatial matrix, just do the verbal matrix, and this is to establish what is your best performance. You can focus solely on these one at a time, so you should be good. Then there were 2 dual tasks. So you would do the visual spatial matrix at the same time as spatial tapping, like this. And the hypothesis here is that there should be dual task interference, because they're both fighting for the visual spatial the visual spatial matrix and the spatial tapping task are both fighting for the visual spatial sketchpad, so they're going to interfere with each other. The other dual task, you did the verbal matrix and the spatial tapping task. Here they're using different resources of working memory, and the hypothesis was that there'd be no dual task interference. Just to show that in pictures, so if you're doing the spatial tapping and the visual spatial matrix, you're going to overwhelm your visual spatial sketchpad, and there's going to be interference. However, if you're doing the verbal matrix and spatial tapping, these are using different resources. There's going to be no interference. You should be able to do the verbal matrix task as well as you can individually, even when combined with spatial tapping. Okay. Here are the results. So what we have here is a score, and this is either out of 8 or 6, depending on whether it was the visual spatial matrix or the verbal matrix. Let's look at single tasks first, shown in blue. So if you just do the visual spatial matrix, this is baseline, this is good performance. And then over here, if you just do the verbal matrix, this is your performance. So you're doing well at both these tasks. Now, if you do the visual spatial matrix and spatial tapping, your performance on the visual spatial matrix has a huge decrease. What we're seeing here is the interference. They're both fighting for the same resource, and your performance decreases. Over here, there's a non-significant change in performance. And why is that? Well, it's because the verbal matrix doesn't interfere with doing spatial tapping, so you can maintain your performance even in these dual task situations. All right, let's just summarize that. So Beach found dual task interference between the visual spatial matrix and spatial tapping tasks. And there's all sorts of tasks that have been looked at in all sorts of dual task experiments that come to the same conclusions. Now there's no dual task interference between the verbal matrix and spatial tapping. This reinforces that yes, these are different resources. If working memory just had one resource and everything was done there, then any 2 tasks should interfere with each other. But because you can do a verbal task and a spatial task at the same time without interference, they must be different resources. Now, a little follow-up here about dual task interference and how this occurs in the real world when things are kind of more complicated than what we saw in that working memory experiment. And you can also think of this, why driving and texting is illegal. And I think intuitively, we agree or we understand why that's the case. And more specific, if we want to fit it within this framework, it's because there can be 2 types of interference we didn't mention previously. So first, is called structural interference. And this is when your body can't do two things at once. So driving, you use your hands. Texting, you use your hands, right? So there's a competition there for your hands. You might think, okay, well, I can use one hand to drive and one hand to text, but you're not going to be able to drive as well with one hand as two hands, and you definitely can't text as well with one hand compared to two hands. The other sort of structural interference we see here is the eyes. So we do have two eyes, but most people can't have them look at different places at the same time. So that's structural interference. If you're driving and texting, you can only be looking at your phone or the road at the same time. Yes, you can look at one, look at the other, look at one, look at the other, but moments when you're looking at your phone, you are going to be missing things, on the road. So structural interference is also a source of interference, and in these studies they made sure that, say, when you were doing spatial tapping, they didn't ask you to also do something with your hand, because they knew you can't do two things at the same time with the same body part. The other thing that can happen is when the tasks get more complicated, they can start overloading the central executive. So yes, the verbal matrix uses the phonological loop, and the tapping task uses the visual spatial sketchpad, but they're both placing demands on the central executive. In that experiment, we didn't see interference because they weren't very difficult and the central executive was not overwhelmed. But in the real world, it's not hard to actually overwhelm your central executive. So let's say you're driving and talking to a passenger. So we'll say that driving uses mostly the visual spatial sketchpad, talking to a passenger uses mostly the phonological loop. And it's possible you can do that if the central executive isn't overwhelmed. But now let's say you're driving in congested city traffic and maybe in an unfamiliar city with, say, one-way roads. That's like my least favorite. So now the central executive is going to be very busy, and you start to debate with your passenger the merits of the Second Amendment. So, very heated debate. So even though, yes, those things require different resources, if they're complicated, you're going to overwhelm your central executive, and you'll still see interference. All right, so yes, interference, dual task interference in the real world, gets more complicated. All right, so we finished our sub-module on working memory, and we now know that working memory has three components to it, and this is being substantiated by dual task interference research. And we can think of our working memory as kind of our workspace. Anytime we want to work, process, think about information, it's got to come to working memory. It could come from long-term memory. You could be thinking about something in long-term memory, or it could come from the external world via sensory memory and your attention. In our next module, we'll finally get to long-term memory. Ooh, one last video. Now, other animals besides humans also have working memory, and the neat thing about it is that their working memory has evolved to be most beneficial for their activities. And we'll see in this case that doesn't actually mean that humans always have better working memory. And in this video, we'll see how chimps' working memory can clearly be better than human working memory in some cases. So take a look at that video, and then I guess that's the end of the module, and I'll see you in the next one on long-term memory.